Assalamu alaikum. Today I give you the lecture on BJT characteristics and parameters. Let's start it. I tell you about the symbolic representation. IC, IB, IE, collector current, base current, meter current, base resistance, collector resistance, base voltage, collector voltage. Same as mentioned. Only the polarity can be changed by NPN, PNP transistors. Beta DC and alpha DC. Beta DC is the ratio of collector current and base current. On the other hand, alpha DC is the collector current and emitter current. Collector current and base current is equal to beta DC, and beta DC is less than 20 or 20 to 200 or higher. On the other hand, alpha DC is always less than 1. It also gives this example to understand what the alpha DC is equal to. This is the ideal model of transistors. When base voltage is forward bias, then collector current passing through the circuit. I already tell you about the current symbols of currents. On the other hand, VB is base emitter voltage and VCB is base collector voltage. VCE is base collector emitter voltage. VBB is always smaller than VCE to operate it. VB is as forward bias, so its value is nearly equal to 0.7 volt. If we apply the Kirchhoff first rule on this loop, then what do we find? VRB is equal to VBB minus VE. VRB, the voltage passing through VRB is equal to VBB, and we minus this bias voltage. Then we get, if we apply the Ohm law on VRB, then we get IBRB, and by putting this value in above equation, we get the base current by these equations. Next, we apply the first Kirchhoff rule in this loop. Then what we find it? VCE is equal to VCC minus VRC, as VRC can be minus through or down by VRC. VCC, when VCC voltage passing through this resistance, it is minus, and then we cross through this voltage VCE. If we apply the Ohm law on VRC, we get VRC is equal to ICRC, and we get the collector current from these equations. Now we get to the third side, which is equal to VCB, which is equal to, as we know that VBE is smaller and forward bias. On the other hand, VCB is reverse bias. So VCB is equal to VCE minus VBE. Therefore, we can find 3 voltage cross this equation. VCB is equal to VCE minus VBE. This example is relative to the above topic. Now next we start the collector characteristics of the curve. There, the VCC and VBB is a variable voltage. VBB is smaller than VCC. At first, we start this. IB or VBB is 0 and VCC is also 0. At this point, both base emitter voltage and base collector voltage is also both are forward bias. If we see that what happened when IB is 0, this is the path of IB. what happen when VCC is 0, then IC do not pass through the circuit. On the other hand, VCE is forward bias. So at 0 point everything is 0. But if we increase the VCC and VCE is not increasing up to the B point. On the other hand, current is increasing very fastly. At reach 0 0.7, which is the potential barrier of the VCE, the voltage is increased very fast, while the current is increased very slightly above due to the depression regions from B point to C point. At saturation region, this is the saturation region, which tells us that IB is slightly increased and VCC is increased very fast. Now, if we increase the IB slightly, then our IB is equal to 0, then it is reaches to the cutoff region. It mentioned already this one for one value of IB. This is only one value of IB. This is IB when 0, then the transistor is in a cutoff region where the IC is slightly or nearly equal to 0, while the VCE voltage is very high. In saturation region, the base meter voltage is forward bias. On the other hand, the base collector voltage is also forward bias. So we do not operate a transistor in this region. We operate the transistor from B to C. This is our active region at where we use the transistor mostly. When we increase very high VCC, then the transistor which is to the breakdown region, which break the depletion and everything of the transistors, and very high current passing through the transistor from VCE. Here we use mostly the different value of IB. As IB is 0, then it start from cutoff region to this there, where VCC is varies from there to there. When we increase the IB, the second line gives us. When we increase more the IB current or VBB, then we get this. Next, and so on. This is the collector characteristics of the transistors. This is an example related to the above topic, which tells us the same position. Now it mentioned about the cutoff region. There, when IB is 0, then this is a small leakage current, ICEO, is passing through the transistors, and VCC is equal to VCE, nearly equal to this. Next, saturation region. I also discussed it above. At saturation region, we increase IB. As we increase IB, IC is also increases through the VCE. When we reaches the saturation region, what happened? IC is not increasing very fast as compared to increasing IB. If we increase IB, IC is not be increasing anymore, or very small difference of increase. On the other hand, IB increase very high as compared to the smaller value. and IC is as a constant. I back to the graph. There, if we increase IB, then IC is also increasing. At B point, the IB also increases while the IC is increased very slightly as compared to the IB increasing. When it increases further, then the breakdown region reaches. From C point, it going to break down. Now we go back. Next is DC load line. DC load line, when cutoff region where IC is equal to 0 and saturation region where IC is equal to IC maximum are saturated. We draw the line between these 2 points, cutoff region and saturation region, and this is DC load line where the transistor can be operated or within the transistor can be operated. We discuss this in next chapter. Next point is beta DC. Beta DC varies from temperature. As temperature increases, then beta DC is also increases. Beta DC depends upon IC. As IC increases, the beta DC is also increases with the IC. If IC is constant, then this will be happening. IC constant and we increase the temperature. Beta DC distance started from there and reach there. The middle state tells us what happened to the beta DC if the temperature varies from minus 55 centigrade to the 125 centigrade and so on. Next point is maximum transistor rating. From this calculation equation, we can find that the both IC and VCC are not maximum at the same time. So if one is increased, other will be decreases. I give you the example. Assumes power dissipation is 500 milliwatts. Then VCC is 20 volt. On the other hand, IC is 50 milliampere. Then the transistor can operate between B to C as given by these tables, and we cannot operate the transistor from in shaded area because our calculation shows this. Okay, next point is this is examples also relative to the other retarding. I think so. The chapter is come to end. Okay. The chapter is not ended. The next point is the BJT as an amplifiers. Now we start this. First we discuss about DC and AC quantities. In DC quantities we use the uppercase of alphabets like B, C, E of subscripts of uppercase in DC transistors. If we apply the DC voltage to the transistor, we use the uppercase in the subscripts of both current voltage. And when we use AC quantities or we supply the AC supply to the transistor, we use the subscripts in lowercase or alphabets in the small letters in both current and voltage. While the internal resistance of the transistor is R prime and The emitter resistance is Re prime. Now we discuss the voltage as amplifier. There we give this input voltage and we get this output voltage. Input voltage is give to the base and we get the collector current is in this form. The both form is inverted or inverted to the one another. When we give the input voltage, highest value of input voltage is the lowest value of output voltage or inverted form due to inverted form. We discuss it more. When we AC input apply to the base current, the collector current is increases. Why? Because we also discuss it in previous topics. If we go back to the previous topic where I discuss in DC form, and when we supply to the DC voltage to the transistor, we get the VC is higher as compared to the VB. So there, if we give the AC input supply, we get our output supply is much larger as compared to the VB or V small v. This Re is the emitter resistance of the transistors. So IB, we know that IB this is equal to IE, the current through the meter, and Re, like that. So while the VC is equal to IC and RC, IC and RC, we get the load resistance, we get the output across the load resistance RC. Next, it mention it about there as IC is equal to IE, nearly equal to IE, due to base current is negligible. So the VC is equal to IERC. Next, it mention it this. There is a mistake. VB is equal to VS minus IBRB. I tell you, this is our VS and this is our VBB. VBB, which is equal to IBRB. RB and IB current pass through the both minus with VS, which is equal to VB, this one, small VB, low. Now it is in the problem of softwares. Sorry, I set it like that. Okay, so VC can be considered a transistor as an output voltage. AC AV is the power voltage gain, which is equal to V output divided by V in. So the V output is VC and V in is VB. VC I get it from there and VB I get it from there. The both value can put in this equation. We get RC divided by RE. RC is the load collector resistance, where we get the output or load resistance where we get the output voltage, and RE is the internal resistance of the AC supply of the transistors. There he discussed that we can read more detail in next chapters. This is the example. Let's we discuss it also. Okay. There he should give us determine the voltage gain AC output voltage from RE. There he give us RE is 50 ohm, RE prime. Internal resistance is 50 ohm. Now Vs supply VB, RB and their VBB. That's mean it's all the conclusion. VB is equal to 100 millivolt. We get on the other hand RC is equal to 1 kilo ohm. Or V out, what V out? Let's see. VCAV voltage gain is equal to RC divided by RE prime. So RE prime is 50 ohm and this one. Then what we get 20 voltage gain. Then we calculate the output voltage. What is the output voltage? V out is equal to AV VB, as we know that V out AV is equal to V out divided by V in. VC is equal to AV into VB. Now there what happened? V out is equal to AV VB, base voltage multiplied by voltage gain. Then we get 2 volt RMS, which is much more larger than as compared to the 100 millivolt. There he give another problems. If the voltage gain is about 50, then what is the value of RC? You can calculate it by yourself. As voltage gain is 50 here and RE is 50 ohm, then we can find the RC. Okay, I give you the hint. Now we discuss about the BJTs as a switch. Now the switch suppression. What happened when IB is 0? That's mean the transistor is at cutoff region and ideally it is act as an open switch. When IB is maximum and it go to the saturation region and it act as a and close circuit. What is the condition of cutoff region? When cutoff region when IB is 0, so VCC in cutoff VCE in cutoff is equal to VCC. Same in saturation region, VCC is very small or VCE is very small as compared to the IC, saturation current. I mentioned it in last. I also give you the detail. I'm going back where this table is mentioned. That is there. We see that this is our in saturation region. This is our the VCC. This is a to this point is only a VCC. On the other hand, I see this saturation region is from A to this point. This all the value is IC from A point to B point. The IC is very high as compared to VCC or VCE. While in saturation region, cutoff region, the current IC is very small, negligible as compared to VCC, which is very high from this point to the there. sorry, I go forward, but it is reaches in that point, and from there to there it is in saturation region while VCC is very high. I go back. So in cutoff from a saturation region, the IC is saturation region is very high as compared to VC and VCE. Or IB minimum is equal to IC divided by beta DC. And next example is also related to this, related to the above topics. You can read it by yourself. A simple application of transistor. Now we use the application of transistors. You read it by yourself. This is not mainly more complicated as compared to other. And now he can discuss about the types of transistors, different types of transistors, and mention it. I go to the next chapter now for amplifiers. Okay, thank you.